In this section, we are going to explore changes in energy and the rates of reaction. What's important about the rates of reaction is that we are always looking at the speed. In other words, how can we make this reaction go faster? But before we do that, let's look at energy changes. First concept that we need to consider is something called enthalpy. That is the energy potential of a system. Although how much energy a system has at any one time is interesting, what's much more interesting is looking at the change in enthalpy. Now, the change in enthalpy we consider as the heat of the reaction. And there is a definition for the heat of reaction. It is the net change of chemical potential energy of the system. Notice we're looking at change. For change, we need to consider the final minus the initial. So it's the energy of the products minus the energy of the reactants. When net energy is released, we call that an exothermic reaction. However, when energy is taken in, it is an endothermic reaction. What is important is that whenever we make a bond, we release energy. And whenever we break a bond, we need to add energy. If a bond is strong, in other words, it has a great bond energy, then you're going to need more energy to break it. But when you make that bond, you also release more energy. Remember that whenever you're making and breaking bonds, the energy required is equal to the energy that is going to be released. So whenever I make a bond, let's take an example. If I'm going to make a oxygen-hydrogen bond, at that point, however much energy is required to make that bond would be exactly the same amount of energy required to break that bond. Just one would be in and one would be. Reminder of two definitions again. So we're going to say endothermic reactions. It's when when a reaction takes in heat. And that means that the reaction actually gets cold. All right? Because it's permanently cold and therefore taking heat away from the environment. So there is a net gain in energy. It keeps taking energy away from the environment. And we say that thermal energy is going into potential energy. Heat from the environment is going into the chemical reaction. An exothermic reaction gets hot. Right, so let's just write that. This gets cold, and an exothermic reaction is going to get hot. That means that the net energy is released and the delta H is going to be negative. So in an exothermic reaction, delta H is negative, whilst in an endothermic reaction, delta H is positive. In terms of a definition, the energy now goes from potential energy into thermal energy. So a chemical reaction puts heat into the environment. We need to know the meaning of spontaneous reactions and non-spontaneous reactions. A spontaneous reaction is going to proceed immediately. However, when you have to add some energy to get a reaction started, it is a non-spontaneous reaction. So an example of a spontaneous reaction is if you were to take potassium or phosphorus and just leave them on a table, they could burst into flame spontaneously. In other words, I don't need to bring a match close to them. But if I now bring some carbon, and you know carbon is coal, so if I bring some coal somewhere and I wanted to break into flames and I wanted to catch a light, I need to first bring a match to that situation, and I first need to bring a flame to the situation before I can expect it to burst into flame. That is a non-spontaneous reaction. We need to add some heat before the reaction will get started. An example of an endothermic reaction is if I take ammonium nitrate and I put it into water, we can actually do that and it will get cold. The reaction is spontaneous and it takes place immediately without any help at all. It takes heat from the environment and it gets cold. Delta H is therefore positive, and we call it an endothermic reaction. An example of an exothermic reaction: hydrogen and oxygen brought into contact with each other in the presence of a flame, you're going to get water. Delta H is negative, and that is an exothermic reaction. This reaction does not occur spontaneously. I need to bring a flame or a spark close to it. You don't need to know the specific reactions, but you would need to interpret what does that delta H value mean. In order for a reaction to take place, you're first going to have to get what is called an activated complex. Most reactions require some energy to get started. That's our activation energy, the starting energy. Once you've got enough energy, the reaction goes on. There is a stage that is reached before the final product, and it is called the activated complex. That is a temporary transition state between the reactants and the products. It's unstable, it has a lot of energy, and the energy is released as we form the products. So as an example, I've got reactants A and B. As they get together, the activated complex, or a transition state, is some sort of combination of the reactants A and B, and the products C and D are somehow bound together before they become the product. So the activation energy is the definition of the amount of energy I need to get up to the activated complex. The activated complex is a transition state. So it is a temporary situation. Transition state. Transition means that it's going to change. It's temporary. And then it is going to become the products. In order for a reaction to take place, I'm going to have all the particles in the right orientation. So for example, let's say you would like to kiss somebody. You both need to be facing each other in order for that to happen. If you had your backs to one another, then you would be in the incorrect orientation for a kiss to take place. Atoms are the same. In order to react, they need to be in the correct orientation to one another. And that is when they can have a chemical reaction. We like to graph this information. So here we've got A and B. They become an activated transition state complex, ABC, D. And you'll notice this graph has potential energy on the y-axis and the course of the reaction on the x-axis. So in other words, as the reaction is proceeding, there is energy. That's what we had from the reactants. They get together. They require energy to become the transition state, activated complex. They then release energy and become the products. Energy is activation energy, the energy required to get started. The energy released is here number 2, and the heat of the reaction is how much energy was the change between the start point and the finish point. And I can read that over there as number 3. This reaction, I am letting out more energy than I put in, so it is an exothermic reaction. I take the energy of the products and I take away the energy of the reactants. Let's say this read 10 here and 20 there. If I took 10 minus 20, I would get a negative value for the heat of the reaction. This is an example, another example of an exothermic reaction. So here I've got 60 reactants. Here I have got 40 products. 40 minus 60 equals negative 60 kilojoules. Sorry, negative 20 kilojoules. The activation energy is going to be 120, the activated complex, minus the reactants. So minus 60, and that becomes 60 kilojoules. Notice energy is released and I have a negative delta H value. Here's an endothermic reaction, and here my reading 50 for the reactants, 100 for the products. Take the products, energy minus the reactants energy, and I land up with 50 plus 50 kilojoules, so that is an endothermic reaction, net energy taken in. Notice I need lots of energy to get started, and I only release a little bit of energy in comparison. What is my activation energy? I take the activated complex and the reactants, and I say 250 minus 50, and my activation energy is 200 kilojoules. Let us remind ourselves of the definitions. We need to know a few definitions for this section. Delta H is the heat of the reaction and is defined as the net change of chemical potential energy of the system. An exothermic reaction transfers potential energy into thermal energy. An endothermic reaction transfers thermal energy into potential energy. The activation energy is the minimum energy required to start a chemical reaction. The activated complex is a temporary transition state between the reactants and the product.